Okay, let's move on to some new material here. Remember I said we were going to be revisiting specific heats? That's indeed what we're going to do. Specific heat revisited. Or if you like, the du dh property relationships. What do I mean by property relationships? I mean how one property changes with another. Okay, you'll see what I mean in just a minute. Okay, let's say we have a system. Let's say we have a system, and the system is undergoing an infinitesimal or differential process. For example, it starts off at the initial state with some specific internal energy U, and in the second state, it ends up with a specific internal energy U plus a change in U. So U plus du. So an infinitesimal or differential process. The system is moving over a small change in properties. Temperature starts off at temperature T and ends up at temperature T plus dt, for example. Okay? So we got a differential process going on here. Let us write the energy balance for this system. It's a differential process, so let's write the differential energy balance. Del Q minus del W is equal to the change in energy, differential change, which is equal to the differential change in internal energy, plus the differential change in kinetic energy, plus the differential change in potential energy. Okay? By the way, before we get going here, this could be specific internal energy or it could be internal energy. Why don't we make things a little clearer here? Let's make this internal energy instead of specific. It doesn't really matter, but let's be consistent with the energy balance that we wrote there. Okay, so this has an internal energy U, and it changes by an amount du over the infinitesimal process. Temperature changes by an amount dt. Okay, so let's apply this equation to the system. Now, let's say, how do we go from one state to another? So let's say this is state 1, and this is state 2. Okay, this is a differential process. This path is really small. I'm exaggerating it. Okay, so we're going from state 1 to state 2. It's a differential process. That's why I have du's and dt's in there. Okay. Now I'm going to put some restrictions on this process. I'm going to load this process up with some restrictions. It's not only a differential process, I'm going to make it isochoric. So restrictions. Number 1, isochoric process. Okay? Now, what does that imply? That implies that the little bit of heat transfer, del Q is equal to m CV dt, and that's the definition of specific heat. Remember, specific heat was defined as, let's see, CV was the little bit of heat transfer divided by the mass of the system times the differential change in temperature for a constant volume process. That's the definition of CV. So I'm using that to point out that del Q, the heat added, differential heat added, is mCV dt. So this guy here is mCV dt, if it's an isochoric process. By the way, if it's isochoric, what's the boundary work? It's 0, no boundary work. In fact, I don't see any wires or shafts in this system. So I'm just going to say all work or differential work is equal to 0. No shafts, no wires, isochoric, no boundary work. So there's no work going on. So this term is equal to 0. Okay? Let me load up a couple more assumptions. Let's say that the system is not moving, it's not accelerating, it's not changing position, it's just sitting there. So I'm going to say dPe dKe, the change in internal and potential energy, those are both equal to 0. Okay? The system isn't moving, it isn't accelerating. So I'm going to get rid of these terms. All right? The key here is isochoric process. That's the key. Okay? That's the key. All right, let's write what we have left. Let's write what we have left. Del Q, so we have M CV dt is equal to du. There's nothing left. There's nothing left. MCV dt, that's the heat transfer, and I have du, nothing else left. Now let me divide this equation by mass. Well, the mass cancels out here, and then this becomes specific internal energy. Okay? Now remember here, this was for a constant volume process. So I do want to say here, volume equals constant, isochoric process. Let me flip the equation and write down what I have. Du for a constant volume process is equal to CV dt. Okay? You give me the change in temperature and the specific heat, CV, and I'll give you the change in internal energy. This is for a differential process. Now, here's the clincher. Internal energy and temperature, specific internal energy and temperature, are both properties of the system. If this were internal energy here, specific internal energy, and this were temperature, it doesn't matter what path I take to go from state 1 to state 2. I could do any path I wanted. So it didn't matter that I took a constant volume process. I could have taken any process, any path between these two endpoints over this differential process, and I would get the same equation. U and temperature are properties, so their changes are not path dependent. They are point functions. So, note, U and T are properties, in other words, point functions. So their change, dt and du, are invariant with respect to path. I can get rid of this. V is constant. I don't need it anymore. So this implies du is equal to CV dt for any process. Box it up. That's our first property relationship. You give me the change in temperature, you give me the specific heat at constant volume, and I can calculate the change in internal energy. Now that's a differential equation. So if I want to get delta U, from state 1 to state 2. This is for an overall process. All I got to do is integrate this. And so it's the integral of CV dt from T1 to T2. Okay? If I want it for an overall process. Okay, so let me just say a few more things about this. Let me write this one more time. du is equal to CV dt. Okay, so let's put a box around it. Now, one last little thing before we move on from that differential equation. It's not valid in the dome. Why? Because property changes can occur when temperature is constant. When you're inside the dome, so here's your temperature and specific volume. Here's your isobar. You can move from one state to another, yet keep temperature constant. So that equation, that property relationship is not valid inside the dome. It's valid for gases and for solids. No phase change. So I will write here, note, not valid through a phase change. What does that mean inside the dome? Not valid inside the dome. If you're a superheated vapor, or you're a liquid, or you're a solid and incompressible, you're not changing phase, you're fine. But not valid inside the dome. Okay? Again, the overall process version of this, if I integrate this equation for a finite, an overall process, delta U1 to 2 is equal to the integral of CV dt from T1 to T2. Okay? So if you want to find delta U, you just have to integrate the property relationship. Now, in general, CV is a function of temperature. It's a function of temperature. Remember, we have these ideal gas tables. Let's see, we had ideal. Let's go to ideal gas. Let's assume we're working with an ideal gas. Let's go find specific heat as a function of temperature. Okay, specific heat, CV, CP are functions of temperature. Okay, so to integrate that equation, you need to know what CP is as a function of temperature. Remember, I think I mentioned this before. If you want to evaluate that integral, you can use this polynomial. It's a fourth order polynomial giving specific heat divided by the gas constant as a function of temperature. And the constants alpha through epsilon are listed here for various substances. Here's air right here. There's air. Okay? So if you want to evaluate that integral exactly, if you want to evaluate this integral exactly, you'll have to find out the relationship of CV as a function of temperature so you can determine what delta U is by the integral. Now, sometimes temperature changes are small. So if delta T is small, or delta T1 to 2 is small, then we can assume specific heat is constant. CV, which is a function of T, is approximately equal to a constant. And so delta U from 1 to 2 is approximately equal to CV, and it'll be some average value of specific heat, like evaluated at the average temperature. T2 plus T1 over 2. times delta T from 1 to 2, okay? So this integral, if we assume constant specific heat, delta T is quite small. We can pull the CV out of the integral, and I get CV integral dt, and that gives me CV delta T from 1 to 2, okay? If delta T is small. All right? So this is our first property relationship. du is equal to CV dt. Specific heat is typically a function of temperature. So evaluating, integrating this can be a little bit tricky sometimes. Usually we just assume constant specific heat when we do most problems. If you want more accuracy, you can either use property tables or you can get a polynomial expression for CV and then integrate. Now there's one more property relationship. I'm not going to go through the derivation here, but I will make it plausible. If instead we do a isobaric, so now let's say we do isobaric. If we do an isobaric process, then the work is equal to the boundary work, which is equal to PdV. Okay? And what I get instead is another property relationship for enthalpy. If I just change the path of integration and make it an isobaric process, I get a dH property relationship. By the way, if it's an isobaric process, then del Q is mCp dt. mCp dt for a constant pressure process. Okay? Do the same exact derivation. I will have a boundary work term. It'll have a PdV in there. And I'll end up with the dH property relationship. The differential change in enthalpy is equal to the specific heat at constant pressure times the differential change in temperature. Box that up. The same restrictions apply to this equation as they do for the du equation. Not valid inside dome, but valid outside the dome. Valid outside the dome. Superheated vapor in particular. And then, of course, delta H from state 1 to state 2 is equal to the integral of Cp dt from T1 to T2. And if you want to assume constant specific heat, you can pull this out of the integral and you get Cp evaluated at some average temperature times delta T. So sometimes for a small delta T, delta H is equal to approximately Cp evaluated at some average temperature times delta T 1 to 2. Okay? Delta T 1 to 2. Now I want to say one or two more things about this. There's two more details I want to go over. So for the isobaric process, where we derive that equation, we have boundary work. If it's a constant pressure process, the system can be expanding or contracting, and it's an isobaric process when we have boundary work. Now, if you have a solid or a liquid, liquids and solids do not compress very easily. Their change in volume is quite small. So for a solid or a liquid, there's no boundary work, and these results must be the same. In other words, for a solid or a liquid, Cp is equal to Cv. Put a little box around that, all right? They must be the same. CB is equal to CP. The reason there's difference between these two, DH and DU, is because of boundary work. If it's a solid or a liquid, there's no boundary work. Okay? Now, one last little thing I want to say, and this applies to ideal gases. Remember, at one point I stated the following. Recall. There's a relationship between CP and CV for an ideal gas. Specific heat at constant pressure is equal to specific heat at constant volume plus the gas constant, R. I mentioned this last time. Let's see how we derive this. Let's see how we derive this. Let's see here. Proof. DH. Remember enthalpy. H is equal to U plus pressure times specific volume. Specific enthalpy is specific internal energy plus pressure times specific volume. So DH is equal to DU plus PV. Okay? Now, let me apply the differential, and I get DU plus D pressure times specific volume. Now, DH is equal to CP dt. DU is equal to CV dt. Okay? So let me write what I've got. Let's write what I've got. Let me move over to the next board. So I got CP dt, which is DH. CP dt is equal to CV dt, which is du. And then I have a D, pressure times specific volume. Now, what if we assume ideal gas behavior? What's pressure times specific volume? Let's write down the ideal gas equation. IGB, pressure times volume, is equal to mass times the gas constant times temperature. Okay? Let me divide both sides of the equation by m. These cancel out, and volume divided by mass is specific volume. So this is actually equal to pressure times specific volume is equal to RT. Let me substitute pressure times specific volume into here. So that is RT. And so I get CV dt plus dRT. Now, R is the gas constant. It is a constant. So it comes out of the derivative or the differential. So this is equal to CV dt plus R dt. Let's write down what I got. CP times the differential change in temperature is equal to CV times the differential change in temperature plus R times the differential change in temperature. Let's cancel out the differential change in temperature. What do I have left? CP is equal to CV plus R. So for IGB, the relationship between CP and CV is CP is equal to CV plus R. Put a box around it. This is valid for IGB. Ideal gas behavior, okay? So if somebody gives you a gas and they only give you the specific volume at specific heat at constant volume, and you got to find the specific heat at constant pressure. Boom, there you go. You can use that equation. All right, ladies and gentlemen, I think we've done a lot today. We've done one example and a bunch of theory. I think you're tired. It's the end of the week, or it's the end of the week for me, the beginning of the week for you. And I will say goodnight.